I'm going to talk about Cadence, and I've been doing this type of work for a very long time because I did asynchronous large-scale systems at Amazon for 8.5 years, and I was tech lead for backend of various queuing technologies, including Simple Queue Service. And then I was tech lead for Amazon Simple Workflow Service. And Cadence is kind of reincarnation of the ideas of Simple Workflow Service, but as open source technology. So I'll start from a use case, and just to give some idea how you could use Cadence in one particular case. So at Uber, we have a lot of services and a lot of use cases which are related to incentives. And one of the incentives we give to our drivers is debit reward. Basic idea is that when you sign up for Uber debit card, the service just checks if a driver qualifies for that, and then technically just goes to some database and marks the driver as eligible, and then just needs to recheck, calculate some statistics, and then recheck if the driver is still eligible every 30 days. Obviously, I'm simplifying that and don't take this as direct implementation, but basic idea is that this process is relatively simple, but it should be long. It's very long running, so these rewards can be can last for years. And let me show kind of the implementation of that if we just go and implement this logic directly. So practically, what we want to do is go and practically here for a year, just practically for duration of 365 days. We want to check eligibility, which in this case is just hard-coded for driver should do at least 20 trips per month and have average rating higher than 4.0 and to stay in the program. And then just go and check the eligibility every 30 days. It's very simple code. You just go, sleep for 30 days, check if it's eligible, activate driver, and if it's not eligible, deactivate and just break out of this loop because we stop checking at this point. He needs to sign up again. So there is nothing complex about this implementation. And obviously, when a driver has a trip, at the end of the trip, a message is received and with a rating. So we need to update trip count and increment the rating sum to be able to calculate average later. Oops. Obviously, oops, I think I clicked too much. Obviously, if you work here in any real company, this implementation is not going to fly because you want it to be highly available. You cannot lose data, and you can have very large number of drivers, at least in case of Uber. But you can be, maybe you're doing different type of transactions. I don't know. You calculate something for your web application or your mobile app. And it would be probably make very good interview question to take this very simple code and convert into highly scalable and reliable application. I'll just show you how you would implement it using Cadence. We use workflow terminology because we originally grew up as from the workflow world. But what we have is we technically have an actor, which is just piece of practically class, an object, which has some state, in this case, these counts, and implements practically the same logic which you saw before. I just rewrote it a little bit, but basic idea is it still has this driver rewards method, which gets driver ID, and while it's not expired, which is the same one year, it checks eligibility and deactivates the driver. So it's a pretty simple code, and the biggest difference here is that it uses workflow.sleep for waiting, and workflow current time milliseconds for getting time. And also it calls the activate, deactivate, not directly on the implementation, but on the interface. This is interface, which has activate, deactivate methods and appropriate annotation. And the reason annotation is there to specify the timeout. because it's remote call. It needs to have timeout. In this case, it's just 10 seconds for those calls. But otherwise, it practically gets the implementation of that interface using the special workflow new activity stub API, and then it can call the activate, deactivate on it. Otherwise, it's the same code we saw before. I'll spend a little bit more time going and playing with this code later, but basic idea is that you can take an implementation which is very simple in memory implementation and convert it to Cadence workflow, which is practically fault-tolerant actor, just doing minor adjustments. And why would you do that? Practically because as soon as you convert this code to use Cadence SDK, this code becomes fault-tolerant, durable, and highly scalable. You can easily have millions or tens of millions or hundreds of millions of these parallel actors running in your service. Cadence will handle activation and passivation of them, so it doesn't mean that it means that they don't consume memory of your workers while there is no activity in this particular actor. You can have a large number of them, and it also deals with all sorts of failures. So practically, this state of this code is not affected if your workers are going down, up and down, or even Cadence goes up and down, if storage is not lost. Practically, if you have receive message on trip, you increment this trip count, you don't need to do anything to persist it. It just persisted by the nature of Cadence. So you don't need to do anything. It's just code which is not linked to any specific machine. It just lives kind of in this service. And then at any moment of time, its state can be recovered and it can continue its execution. So to achieve that, Cadence practically implements task queuing. It implements durable timers. It persists states. Currently we use Cassandra, but we are finishing up the SQL implementation to be able to run Cadence on top of any SQL database. And we provide visibility APIs to look into the state of these executions. And the service itself is written in Go, but we have Go and we have Java client-side library SDK, which I'm showing you. But you also can write these actors for flows in Go. What's important about these client-side libraries is that they're practically stateless. You don't need to, besides Cadence itself, and at Uber, Cadence is hosted by our team. So it means that any other program team, which actually implements real business logic or their use cases, they don't care about persistence. They just connect to our service the same way you would connect to any AWS service. And then it's all of this service is managed by another team. So it hides and simplifies life of our engineers big time. Here I show the topology of deployment. So basic idea is Cadence is service which keeps state, queuing, and timers, but it doesn't contain any logic. It doesn't contain any workflow logic, like this actor logic, or what we also call activities, which are practically functions which you can invoke on external world, which how affect external world. Because in this case workflow, it actually keeps state and it can communicate to other workflows, but it actually doesn't affect external world directly. It always affects external world for activities, which are practically separate sets of workers. They are similar to, for example, Kafka consumers in the sense that they connect to, like the same way this Kafka consumer connects to Kafka queue and then consumes messages and it performs any work. The same way activity worker connects to Cadence. If there is a special queue inside of Cadence, it will consume messages from it, process them, and then acknowledge them back once they're processed. The same way a workflow worker will take special messages, process them, and reply back, but it's all hidden from you by the library. From your point of view, just write this fault-tolerant code and it executes. And also there is another role here, it's workflow starter. It's the one which actually initiates instances of those actors. So practically in this case, you will start a driver rewards workflow for every driver. So if we have tens of millions of drivers, we will have tens of millions of those workflows living in our system. So how is a workflow is executed? Just to make it, because I'm kind of talking in abstract terms. Now I kind of show how these all these components do interact between each other. First, some program, in this case, probably website or application, mobile application. When driver signs up, he presses a button, and some backend service will go to Cadence and practically call, make API call, which is start workflow driver rewards. Cadence will create some some state related to that workflow, and also atomically it will put message in a special queue. So this is Cadence is fully consistent service. So all interactions are transactional, and it practically doesn't create race conditions between, for example, the state update and the putting message in a queue. Anyone who tried to write a long-running business logic on top of, for example, database in a queue knows that even just as simple transition as putting message in a queue or in database, in which order you put them is practically impossible to get right, unless you have transactional update across both, which is very rare. And most people don't prefer not to use two-phase commits for these reasons. So after workflow is started, it just state inside of Cadence and message in a queue. But usually there is a workflow worker running, which contains the code of the workflow definition. This worker listens on that queue. In this case, this queue has name rewards. It will get that message, which contains the type of the workflow and input parameters. It will find appropriate function, which implements that workflow, and starts executing it. And as it's practically, it doesn't affect the world directly. It always returns commands, so-called decisions, back to the Cadence. In this case, it will start executing this code, and at some point it will hit workflow.sleep for 30 days. And what it will result in is that it will practically go back to Cadence and say start timer for 30 days. Cadence doesn't have any limits on the length of those timers, so you can set timer for a year or more. Obviously, you need to support a service and run it for that period of time, but there are no any practically hard limits on the duration of timers. And then it will practically logically workflow will get blocked on that call. And when Cadence receives this call, it will update the state, create the timer, and just do anything. It won't do anything else. And this workflow worker will sit idle unless there is another workflow to work on for whatever 30 days. But in real life, as you have millions and millions of drivers, it's always busy. But it doesn't need to be up and running all the time. But in 30 days, this timer will fire, and Cadence will update the state of the workflow, and it also will create the message, again, for that workflow worker to pick it up. So it will pick it up later, and then it will continue execution. So it will go and execute the next command after the sleep, check eligibility, and then it will practically call activate. In this case, it will return a decision back to Cadence, which is schedule activate rewards activity. And it will say that put it in activation queue. Like we call this queue task list, but it's essentially a queue. And after it's done, it practically workflow worker can go and sleep again without doing any work. It's assumed that there is an activity worker listening to that queue, and it doesn't need to be always available because, again, it's a queue and messages can pile up there, so you can have big backlogs. But if it's up and running, it will get that message. Message will contain type of the activity, which in this case activate. It will contain argument, in this case driver ID, execute it, and while it's executing, the workflow worker can obviously fail. And it actually can fail at any moment. I'm just showing it in this presentation that it fails while activity worker is executing. But the important thing is that there is no problem if the state of the worker is lost, because it will be recovered as soon as worker comes back. But in this case, activity worker, even if a workflow worker is down, still can complete its activity and report back to the Cadence that activation is done. If Cadence is up and running, it will go and update the state, create the message for workflow, but as it's not available, this message just will sit in a queue. But sometime later, it will come back, get that message, recover its state where it was, after the activate completed, And in this case, it will go and emit another sleep for 30 days because activation is finished. And at this and practically, you see that there is this interaction kind of dance between workflow worker and activity worker, and multiple of them if necessary. They can be linked to multiple processes, so a single process. But basic idea is that any moment of time, a workflow state, this actor state, can be pushed out of memory, out of cache, and it can be recovered as soon as it's necessary to actually make the next step. And when it's recovered, it recovers the state of every variable in every part of the workflow. Feel free to type. I'm not sure if you want to ask questions directly or type them in the chat. I don't see any questions so far. So now I will just explain how recovery happens, and then we probably can take more questions about it. So the basic idea is that we use so-called event sourcing to recover workflow state. How do we do that? We record all external events which happened in the system in a so-called history, execution history. So when you call start workflow execution, we will record workflow execution started event, which contains workflow type and input of the workflow. And system will schedule decision task, which is the task it puts in the appropriate queue for workflow to pick up. So it will record decision task scheduled event. As soon as worker picks it up, decision task started event is recorded. It contains worker ID, so you can always find which worker picked it up. And then when workflow requests timer, it will record timer started, and then in 30 days, so there is 30 days between event 4 and 5. Timer, obviously real history contains timestamps, so you can look at them. Timer fire will be recorded, and then and so on and so on. So when activity is required, activity task scheduled is requested. When it's picked up by worker, activity task started is requested. When activity is completed, activity task completed is recorded, and so on. So how do we use this history to recover the state? We just start working that history. So workflow execution started tells us which function to execute and the input argument. So we find that we find the appropriate object, instantiate it, and start executing it. At this point, the state of this object is not up to date because it practically contains all variables will be 0 because they are the same state as it was before, like initially. But we start executing this code, and at some point we will hit a workflow.sleep, which practically corresponds to start timer 30 days decision. And at this point, this code blocks. It's a block and call. You can also have asynchronous timers and futures, but in this case, it's just block and call for simplicity. And in this case, the workflow cannot make any progress. But we can, but we have history, so we can start working the events in the history. And at some point, we will reach timer started event, which actually corresponds to start timer decision, which was done because we called workflow.sleep. What does it mean? It means that this decision was made before. So it's duplicated decision, and it can be ignored. And we will remove it from the list of decisions. Later, but as we are still, workflow is still blocked, we keep running, we keep working the history. And we find timer fired event. Timer fired event unblocks the workflow.sleep call because it tells that 30 days passed. And then we can start executing workflow code again. It will execute until it hits driver rewards activate, which is activity call, which is block and call. And it also responds to a decision, schedule activity, activate rewards. And at this point, workflow is blocked again. And then we need to start working history. We will work history and find activity task scheduled event, which again will dedupe the schedule activity decision. Then we will reach activity task completed, which will actually contain a result of activity rewards activity. In this case, it does, in this sample, it doesn't return anything, but in a lot of activities can return any data. So then activity task completed would contain the result, and we will unblock that call and populate whatever result and continue execution. In this case, execution will go until it reaches the sleep. I think I have kind of bug in my highlighting, because it should block on sleep, not expired, because expired is not blocking call. But after we blocked on sleep, so which corresponds to start timer event. So on the left, it should highlight sleep. And we walk the history. Workflow is blocked. We have no events in the history. What does it mean? It means that we have start timer decision for 30 days, which should be sent out to the server. And in this case, worker is blocked, and it will send out this decision. At this moment, the state corresponds to the current state of this workflow or actor. But at this point, it can be safely lost, because anytime it can be recovered again. That is kind of the basic idea how we do recover the state. Question, okay, that is a good question. I'm checking. Curious, how is it related to AI? I'll go to the next slide. So practically, AI is, I'm not an expert in AI, right, and AI algorithm. But one thing I know about AI, that AI is about big data, is about a lot of computing resources, is about training, is about long-running processes, because to train a big like model, it requires a lot of coordination, and you also have pipelines. And for example, in a lot of cases, you want to automate training and retraining based on new data. And Cadence is exactly the way you would orchestrate and support practically long-running processes to train your pipelines. Because it's like I've seen cases when people try to do this orchestration for scripts, through database calls, through like they try to use workflow engines like Airflow. The problem is those engines that they are not they have a lot of limitations. For example, in these cases, you have this actor model. This object can have any state. It can receive any events. It can react to that anyway. You can have multiple threads inside of that object. So you practically have you can implement very complex orchestration logic to train model. Versus like if it simplifies your life comparing to, for example, trying to do it for scripts or any other technology. So I'll go back to the use cases. So some other features which I didn't mention is that Cadence supports cross-data center applications. So you can have multiple Cadence clusters in different regions, for example, AWS region, so data centers, if your company has multiple data centers. And you can practically fail over workflow, your practically execution of your workflows from one data center to another. It means that if you complete loss of data center, doesn't mean that you will lose your workflows. They will continue execution from the way left off in a different data center or region. I don't think any other workflow technology supports that the way we support it. And you can do more than 2 data centers. So practically you can have one active data center, and it's pure namespace. We call them domains. So if you have multiple use cases running on top of Cadence, each use case can decide in which data center they want active workflows. We support signals, which is practically the way to call into the workflow asynchronously. So you can practically listen for some Kafka events. And this is exactly the on trip would be a signal. And actually, if you look the actual implementation of the interface of this workflow, it has it marks on trip as signal. So it means that it will be received asynchronously from external system. So in our world, we have Kafka, and we will just listen to Kafka's stream and call on trip on every new trip completion event. We also support queries, which is the way to query workflow state out of the workflow anytime synchronously. So practically, if you need to learn what's status of like state of this workflow, you can just have multiple query methods and return any business level information about them. Child workflows, obviously, we want to not just one workflow actor. We want to have a hierarchical, create like children. So you can have, for example, if you need to run million of tasks, so just have, for example, million drivers, but you want to start all of them together, you could have one parent which would go and create children, and for example, hierarchically, like, I don't know, have one child per city, and then in each city have, I don't know, this one will have children. There is a limit on the size of every workflow, but a few thousand children up is possible. If you need millions of them, you will probably do more like a tree. Like a child will have like 1,000 children, and then it will have another child, 1,000 children. You already have million. So that is the way you would create like large applications which are controllable for a single parent. Task routing. In a lot of scenarios, it's useful to implement, to route execution of some code to specific host or even process. For example, we have sample is, and a very common example is media encoding. So for example, or actually it would be useful in ML case when you need to download more. For example, you want to download some file from S3, you want to encode it, or for example, run some transformation on it, and then you want to upload result back to S3. So it's kind of three-step flow, like download, transcode, upload. But if you have a fleet of machines, the first action can run on any of these machines, but second and third should run on the same machine as the first one. And again, if machine goes down, you need to replay the whole sequence from the first. And you can do it easily with Cadence, because Cadence supports routing tasks to specific machines when necessary. That is a very important feature. Heartbeating. When actions can take very, very long time, and I'm talking activities in this case, these like external actions, unless you support very long, we don't have limit on the execution, but unless you support heartbeating, it's not very useful because it will take very long time for them to time out. Everything is protected by timeout. You always have to specify timeout for every operation. But if you want to get error earlier, you will just ask to heartbeat. Also in heartbeat, you can piggyback progress. So it means that if you're, for example, processing records, you can say, okay, I process record 100, process record 200, 300. And then when, for example, if host goes down or task dies, the workflow will get error, and then error will contain the last progress. So it can restart that from the last progress information. So it's useful. Visibility, you probably can get a lot of information about the process. I will show you some UI, like how you do it for UI or CLI to get information. List workflows, you can, like, for example, list all everything in flight, all failed ones, all open ones, and you get status about each of them. So also, as we use event sourcing, these workflows are highly debuggable, because you practically, if you got failure in production, you can just download the history, fire up your code in debugger, and just replay that history in debugger as many times as you want to reproduce specific program. And we also have a lot of other interesting features, like, for example, getting stack trace of any workflow in production for UI. Looking at questions. IoT, actually, yes, we are actually talking to, we actually had talks to IoT guys. I don't want to name companies, but practically some of big companies are interested in IoT space because it's exactly, you can have instance of this workflow actor per device, for example, and manage its life cycle. And Cadence ensures that it never practically, it's always up and running, and there is no reason, you never lose state. And everything is protected by timeout, so you can always make progress and make sure that it's highly available. So let me just give you some demo, and then just to show these features, and maybe it will become more clear, less abstract. So practically, let's go back to this example. So let's start from activities. Practically, first you define actions, and not all, you don't always need actions, because if you're doing just aggregations, but at the end you still need to, for example, notify about the result of your aggregation or update some external system. In this case, our external system has only two API calls: activate and deactivate the driver, right? And we also need to specify timeout, because every kind of external calls, we want to make sure that we make progress if it fails and we retry it. We just launched in production the automatic retry on the server side, so you could specify exponential retry policy, and then these calls will be retried as long as necessary just by the server without you practically just specify the retry policy, which is options. So to implementation of this interface can be anything. It's your code, it's just a plain old Java object, and in this case, I just do very simple print, but it can be any call, it can be very long running, it can heartbeat, but it's anything. There is no any. You also instantiate this object when you register with our worker, so it means that you can inject any dependencies, connections, service clients, whatever, into the activity implementations. If you go to the workflow, workflow is kind of similar in the sense that it's defined by interface, because when you start, you call a method which has not data with workflow method. Workflow has execution timeout. In this case, I have it like 365 days. And task list is the queue name, which is practically we use to dispatch tasks to that worker. And activities also have task lists. And workflow can have other two types of methods, which is signal, which is asynchronous calls into the workflow, and queries to query status of the workflow. Let me check if there are questions. How easy to set up? So it depends. Okay, I'll answer this a little bit later. Let me finish the example, and then I'll go to the setup questions. So let's look at the implementation of the workflow. Practically just implements that interface which I defined, which had this on trip, get rating, and driver rewards methods. And this is just object. It can have any data structures here. The only requirement, because we use event sourcing, that this code should be deterministic. That's why you have to use workflow sleep and workflow current time milliseconds, because when we replay this code, we give you time as it was at the time when this code was executed for the first time. But otherwise, if this practically all Java data structures deterministic, you have hash maps. For example, if I decide to make a sample more complicated and, for example, dedupe messages here, I would put, for example, set and dedupe because Kafka doesn't guarantee uniqueness, it can deliver the same message multiple times. But we can put trip ID in a set or hash map and make sure that we dedupe our, for example, ratings. And it will be just very simple in-memory data structure. So how do we run this code? So practically to run this, we need to create a worker. And this is practically the whole full example of starting a worker. So there is a worker factory. You need to specify domain, which is just namespace. Practically, that is every customer, every use case gets its namespace. So all IDs or all task list names and everything is scoped to a domain. So because we are multi-tenant service, it's kind of similar to Bucket, for example, in S3. And then you just create worker. We're using worker and task list, which is kind of queue name, worker listen zone. And then you just register workflow implementation type. You pass class object down. And because we want to control the life cycle. But for activities, you actually register instance of an object. So here you can inject any dependence into an activity. And it means that you can use whatever injection framework if you need to. And then you just call factory start. At this point, worker is running. So let's try to run it. So it just printed worker started. And nothing happens because worker is running and listens on this queue, but there are no tasks in that queue because there are no instances of the workflow. So to create instances of the workflow, we need to practically have a separate program, or it can be separate part of your code of the same program. It can be in the same code. And in this case, you will practically create new client and again, pass in domain. And it's here's the simplest default client. It will connect to the local instance of the service. I have service running right now in a Docker container. So it's kind of about answering question about how easy to set up. If for local development, all you do is Docker compose up. Practically, I have run it in a Docker. And if you look okay, it's scrolled up. But practically, it's Docker Compose up, and it will just download all the necessary Docker images and start them. You will have a fully complete instance of the service running on your machine. So for development. Oops, going back to code. But then this client, all you do is to practically say new workflow stop, passing the type of the workflow interface, and options. In this case, we use options because we want to set the workflow ID to the specific driver ID. Why do we want to do that? Because Cadence guarantees uniqueness of the workflows. So if you specify ID, it's usually your business ID. In this case, we use driver ID. Then it means that you never will have a problem with running multiple of them, because Cadence can guarantee that you can run only one at a time. So it's in this case, we use options to do that. But there are some other options like timeouts and everything you can set here. And then you just start. You can call actually workflow.driver. You practically can call code like that. But then this code will block until workflow is done. You probably don't want this code block for a year. For some cases, for short-lived workflows, it does make sense, especially during development. I like to do that because this returns a very clear exception if workflow fails into the calling code. But in this case, we use practically, we pass the reference to the method and call workflow client.start. It starts it asynchronously. So in this case, you don't need to wait for workflow to finish. It just returns immediately as soon as workflow is accepted by the Cadence system. So let's try to run this code. So it started. So, okay, it started, but how do we know what's going on? So we can go to our UI. Look, this is localhost 88. So this is actually part of the Docker image. The UI server is also part of the Docker image, so you get it for free when you do Docker Compose up of Cadence. And let's just look, let's refresh. So we have one open workflow. Its workflow ID is driver. Run ID is because you can start workflow multiple times the same driver ID if you specify appropriate policy. You can specify that you don't want to do that, but sometimes you want to run it multiple times. So every time you run it again, it will get different run ID, which is just UUID. So if you click on that, we will get information about this workflow. First, we know its type, when it started, and then task list is on, which is the queue, our workers listen zone, and also the input. In this case, it just had one simple input. But if it's more complex structure, it will appear as a serialized JSON. And then other interesting thing is that, look at this, we have stack trace. So we are waiting, right, on line 33, which is in this case, is exactly workflow.sleep, right? The other interesting thing is that if I try to run it again, now we have two workers, which kind of makes it fault tolerant because any of them can die. But let's for now just go and kill both. So and then start it again. Actually, let's do the other thing. Let's go and start the start workflow for driver 2. Note that my workers are down, but oh no, I started working. Sorry, I started working again because I did. So workers are down. Let's do run starter. It still started. If you go to UI, we will see two of them, driver 1, driver 2. So let's restart the worker. Okay, worker restarted, and let's go and check the stack trace. It's still waiting on 33. So practically, our workers going up and down don't affect the status of our workflows. You still can get stack trace, you still can do query, for example, and let me check if there are any questions. So do query and communicate with them. So there's main advantage of using Cadence is that your code just becomes fault tolerant without need to write any code. Actually, I just saw that there is a question about unit testing framework. Okay, I'm kind of prepared there. This is unit test. So the coolest part about unit test framework which Cadence provides is that just look at this. We just what we do. We mock activities implementation, which is just activities again is our interface with activate deactivate method, right? So we just use Mockito framework to mock them. We register the mocked activities with worker, and we instead of the default factory, we use test environment factory, which is let me show. It's a test workflow environment, which is just a new instance. And it is like that factory, it just this test support. And then you just say test environment, new worker, it creates a worker. And then you do the same thing with the worker, register workflow implementation type, and you can create new clients and so on. But look what we are doing here. We create new workflow stub, and we start it asynchronously the same way. And then we do interesting thing. We say sleep for 32 days in the unit test. And then we say verify that deactivate will call once. Why? Because this driver never had a trip. And then we have test for activate. We do the same thing, but then we sleep for 1 hour and then we report 30 trips with rating 5 every 30 minutes. And then we assert that we get the rating, we make a query to the workflow for the client API. Rating is 5. Right, and then we sleep for 32 days and we verify that activate was called. Let's try to run this code. Okay, it took longer than usual, but practically, usually under 1 second, you get this test spicing. How does it happen? So the workflow test framework practically runs inside of the Java process. The mock practically let's say very simple in-memory implementation of Cadence Server. But this implementation understands when your workflows are stuck, waiting on the external events. At this point, it just goes and skips time automatically. You don't need to do anything. It just says, okay, everything is stuck and it's waiting for 32 days. Let's just skip this. And then it will go and automatically advance time for the time it sleeps. So practically, it allows you to keep to test your very long-running logic in milliseconds. Without practically requiring you mocking this, you know how usually you do that. You need to write your logic differently for the unit test and not for unit test. In this case, I didn't modify workflow at all. It had sleep for 30 days, and we asked our test framework to sleep for 32 days, and it just did the right thing. Okay. Going back to the UI. So other part, remember I told you about history, which shows how workflow we record. So you can see that history in the UI. So practically this is the, in this case, this workflow has very short history because all it did, it was started. And again, we see all information about its start. We see the input arguments, in this case, driver 2. We see timeouts and everything. And then we see the decision task, which is workflow task, was picked up by this process on my laptop. And then it was completed and timer was scheduled for this period of time, which is, I remember, is like 30 days. And this is it. In this case, it will just keep sleeping for 30 days. I can modify this. Let's to make this a little bit more interesting, let's go and call that onTrip method. Because onTrip is marked as signal method, we can call it practically, oops, sorry, I jumped wrong place. OnTrip is marked as single method. We just need to send signal to the workflow. We can do it through the client, or we can do it through actual CLI. So Cadence has CLI, and we can go and, not here. Yeah, here it is. So we just need to change ID of the workflow to driver 2. And let's say we send signal to that. Let's look at the UI. Signal driver 2. For some reason, I don't see it's updated. Let me see. Okay, it probably got cached. But basic idea, you see, we see a workflow execution signaled event in the history because it was just waiting on timer started, right? But as soon as we've got workflow execution signaled, we see the, again, input to the signal can be any data structure. And then at this point, it just got processed. But right now, if you go and run query, again, we can do it through API, or we can just do it through, you see the query type is just the name of this method. It will actually return us that average rating of the driver is 5.0. So, but you can add as many, let's just for the sake of, let's add 1 star and get the average. It's 3.0 at this point. So practically this object, and the other part is as well that we can kill this worker anytime. Again, just to emphasize it on it again. And at this point, you can send signal because signal goes to Cadence Service, but query will fail at this point. It will time out because worker is not running and it cannot reply. But as soon as worker comes back, it replies with appropriate result. Okay, let's look at questions. Okay, I think it kind of explains basic idea. So it just code, it represents very simple interfaces. There are certain rules you have to follow, but they're not very complex, right, in these workflows. They are fault tolerant, your workers can go up and down anytime. And you can communicate with them through queries and through asynchronous signals. And obviously you can do anything you want in this, like your logic as complex as necessary. You can use object-oriented design, multiple objects, these fields can be as complex as necessary, not as ints. It can be complex objects. Going back to presentation. Okay, going back to use cases. Almost everything which is long running fits this use case. After you kind of get used to this platform, you see that a lot of use cases just match that. Most trivial one is persistent timers. For example, you want to run something once a day across fleet of machines, and you have all these visibility features and execution history. So it's it's very common use case at Uber. Sign up flows. For example, somebody signs up for your website and you want to do background checks. Or for example, driver sign up at Uber is very complicated workflow because every city has its own rules about it. Order fulfillment. I've heard that Amazon uses simple workflow service for something like Amazon, I think, delivery of the similar to Uber Eats, I think Amazon Fresh. Big data control plane, ML pipelines, as I said, that all of them require long-running tasks to control them or do recovery of them. For example, if your pipeline, like some node dies, you need to reprovision that. Automated deployment. Uber has deployment system, and right now we are porting that system to Cadence. Customer-facing communication flows. For example, we have a system inside of Uber, which is a yes/no type system, which is if driver had that many trips and that rating, send them that message. If he had low rating, send them another message, things like that. So you can have kind of this DSL, or UI, which describes different flows of communication and marketing messages to your customers. Customer service. So customer service is one big workflow because you need to go through multiple steps, automatic validation of tickets, and then you also have humans in the chain, which can take long time and also create some actions to execute. I mentioned already IoT. Page flows, they have star. So one feature we kind of support but not support directly yet is synchronous transitions. When you practically call into the Cadence and says, give me next step to execute. Then you could do practically wizard type page flows in your mobile application or web UI. We are planning to add support to that relatively soon. So then you would be able to do not only asynchronous background workflows, but also synchronous flows of information and still do some background jobs at the same time. Okay, let's go back. So practically this is the all material. I have a lot of, okay, summary. So practically Cadence is task execution service, and also like state, it keeps state of your execution, and model is practically fault-tolerant actors. I know that people, when we hear about workflows, they usually start thinking about domain-specific languages, YAML, JSON, XML. There are a bunch of them, BPMN, and so on. You can easily implement them on top of Cadence because you just write interpreter using the Java or Go language, which we support directly, and then they become fault-tolerant in the long run. We have multiple, for example, if you want to consolidate all workflow systems, existing workflow systems in your company under one execution engine, you can do it easily with Cadence. This is what we are doing right now at least at Uber. It was inspired by Amazon Simple Workflow Service, and it's scalable, fault-tolerant, and open source. So you can download and change it and play with it right now. Okay, going back to questions. Let's start. Version, yes, very good. Let me start from, yeah, version support. So yes, it's challenge because doing versioning long-running business process is non-trivial. And there are various ways to solve that. There are trivial ways, for example, use versioning, and it's very easy to do versioning with Cadence because you specify task lists, which are these queue names when you start workflows, so you can have multiple versions of them running in parallel is no problem. But it only works for short-lived workflows because then you need to have multiple instances of the workers running. Our solution is different because, for example, if you have a workflow which runs for half a year, you started it yesterday, and then you find bug which this workflow will hit 5 months from now. Even if you deploy a new version with the fix, the workflow which was started yesterday still will hit that bug. So versioning, like simple version, doesn't work there. What we do, we actually provide API call, which is called get version. Let me just find it, a Java doc for that. So practically, basic idea is that, let's say you had a code which was like, okay, call activity 1, right? And you need to change it to call activity 2 instead. Practically, as we use replay to reconstruct workflow state, we cannot just replace it because it will break determinism of the workflow. What we do, we give you a get version API, and practically, if it returns the default version, which is not versioned one, you will run the old code, but otherwise you will put new code. So workflow will always use new code unless it replace and it was using old code before. This way, you can have multiple these conditions because they practically have the ID in different places. You can even have library, for example, which you give to other people, and they can put in their workflow at any time. And then you will be safe doing upgrades to that library if you use this mechanism because you don't control which version and when they run, but it will just contain all versions of the code. If you do control which version they run, you start removing all conditions practically as soon as the old workflows which used old code drained. Usually you know the maximum duration in your workflow, so you just usually say, okay, my maximum workflow takes 1 week, so after 1 week it's safe to remove the first branch. You obviously can have more than one branch. You can have like as many as you need. We also perform checks. So if you by mistake, for example, remove the branch and keep running, workflows will not fail. They will just stop executing. They start throwing errors saying cannot make progress because the non-deterministic change, the version, not supported version. So that is the way we can do the versioning and upgrades of the workflows. Okay, going back to the questions. How easy to set up? So practically, for development, as I said, it's just Docker container. For production, it's also a bunch of Docker containers. We obviously deploy them using Mesos, or you can use Kubernetes. I think one of our customers uses Kubernetes to deploy them. And from backend, the only supported database right now is Cassandra. So if you have Cassandra cluster, all you need to do is practically run the script which will install schema, and then configure your containers to point to that Cassandra instance, and this is it. You don't need to do anything in some additional config, but this is it. So it's very easy to set up. We have multiple requests to support SQL, so this is what we probably will deliver pretty soon. SQL support. Then after that, practically any SQL database would do. And otherwise, it's just, again, Docker containers to run. For the service itself, your workers, I showed you Java code. This is like few lines of code in your Java application to associate those workers. Okay, I answered the question about test frameworks. I talked about versioning, how data get persistent. Yes, it's persisted in Cassandra right now. But again, when you run it as a service, then usually, at least in most big companies, we expect that will be team managing the actual service as a deployment, and then a lot of other customers will just use that service the same way use AWS services, just pointing to that service front ends. Let me see if I can join the. Oh, it's complicated. You can ask questions on the microphone if
No, actually, I mute. They probably cannot talk on the microphone.
Oh, I see.
No, but they can type on the chat window. By the way, I saw you just join the Slack channel. So
I don't yet because it requires verification.
Yeah, that's how the Slack works. You need to verify a couple of times.
Yeah, let me see.
I see another question coming, say the difference with the Airflow.
Oh, okay. Yes, obviously. So practically a couple of things. The first, Airflow is Python-based, right? If I'm correct. The biggest difference is, like, there are multiple. First, scale. We are targeting scale of execution or creation of like 1,000 workflows per second. At least on our Cassandra cluster. So practically, we want to be able to execute business level workflows. Airflow, is, as far as I know, has problem with a few thousand, and we want to have billions of parallel workflows. So Airflow is just a completely different scale. It's a first thing. Like, just there is no way you would like use Airflow for something like, for example, these incentives I talked to you about. Just because you cannot have like 20, 30, 50 million parallel instances running. Other thing is that just execution model is because it's a Python code from one point of view. From other point of view, you execute this Python code to create a graph. And after this graph is created, the graph is fixed. Even like practically, you are very limited in what type of business logic you can implement in that graph. In this case, it's like Java code or like Go code. You can do anything you want there. You just, there are very few things you can do. You can do as many parallel branches as you want. You can run a very complex logic. You can have state. So it's much more powerful. Other kind of way to put it is that you can absolutely easily implement Airflow DSL on top of Cadence. So if you want to, for example, use DSL, you have Airflow and it doesn't scale right now at your company. You can go and implement a domain-specific language, practically take Airflow and just write interpreter, for example, using Jython on top of our Java client. And then you will get practically Airflow workflows will start running on top of Cadence, but then you can get really large scale. And then you interoperate with other Cadence workflows easily. So that is kind of the basic idea. We have